good morning. So we shall continue where we stopped last week. I think we stopped somewhere around here last week. We started looking at eutectic system, binary eutectic system, and we said that what eutectic means is that you have the lowest melting temperature at that point. When you have the two alloys, the point at which the two alloys have the lowest melting temperatures. For example, you can see this one here. You have lead. The melting temperature of lead here is about 340 or 50 thereabout, while the melting temperature of tin here is about okay, let's not use Fahrenheit, we're using degrees, is about 200, and if you draw it to the left, it's about 230 also. So, but then we have the lowest melting temperature, which is even lower than the two melting temperatures of the alloy of the metals. And we have the lowest melting temperature at 183 degrees. So this is eutectoid and eutectic, sorry. And this is the point at which there is a transformation from liquid to solid, direct. You know, when you move from anything apart from this point, it will have to pass through the two-phase solid and liquid region. These are the two regions, solid and liquid. But this is the point whereby the moment you cross, either by heating, you will have a liquid, or by cooling, you will have a solid. I said this is eutectic. We are going to continue with binary eutectic. You know, we started it last week, the binary eutectic system, and this is the system here. Why we call it eutectic is because it's the point at which you can have direct transformation from liquid to solid, or from solid towards liquid, upon heating and upon cooling. So today basically we are going to do some calculations. This particular structure, we call it eutectic. And when we move to the left, we will still have this structure, and we will have additional alpha in a kind of spherical form. I've said it earlier. This is when we move to the left, you will have additional alpha in terms of this ball, because here alpha is representing blue, while the beta is representing, is it brown or red? So as you move leftward, because alpha boundary is leftward and beta boundary here is rightward. So when you move leftward, you will have additional this same structure, which is alpha plus beta, with additional alpha as in this spheres, right? As in this sphere's blue color. And when you move to the left, you will still have this same structure, which is the background, with the additional beta, which is represented as as the brown or red spheres. So let's look at these questions and see how we can solve them. Question number 1. The first question asks us a 3.46% by weight tin of. So understand the question, know what percentage is the alloy. First, we'll be given an unknown alloy, and this alloy here given is okay, you may be given either a known alloy, right? And then you'll be asked to determine the percentage fraction of the constituents. And it says a 34.6% by weight tin of lead tin alloy is cooled below the eutectic temperature at 183 degrees. What is the fraction of the peritectoid and eutectoid mixture? So this is question number 1. Already we have so don't worry, here is our 61 point lead tin. So remember, the first thing you have to, your boundaries. Boundaries are very important. You are going to be working on boundaries, right? Either the alpha, beta, and alpha plus beta boundary. This is the alpha boundary. This is the beta boundary. So let's look at the question again. It says, what is the fraction of pro-eutectoid alpha and eutectoid mixture? So the question is asking us a boundary between alpha and alpha plus beta. In this case, this is our alpha plus beta boundary, because this is the only place you will have alpha plus beta at 61.9. So this is our alpha plus beta boundary. In this case, we only have two boundaries, alpha and alpha plus beta. So our boundaries are going to be what? We are going to be working within these two what boundaries. What is our alloy composition? Is 34.6. 34.6 will be somewhere around here. This is our alloy, 34.6% by weight what? Tin. So what is temperature? It means we have to locate the composition, the alloy, and the temperature. Remember, the whole of this region is alpha plus beta. Remember, all this region is a region of what? Alpha plus beta. But we have different types of alpha plus beta. So in this case, we will have, at only this point, we have alpha plus beta at 61.9. So when we have it to the left here, when we have it to the left of 61.9, it means we are going to have alpha plus beta. When we have it to the right of 61.9, it means we are going to have alpha plus beta plus what? Beta. So these are the only several combinations, 3 combinations we can have of this alpha plus beta blue region. So now we have to determine our temperature. You know, whenever you have the alloy, you determine the temperature. This is eutectic temperature. Eutectic temperature is at what? It says it is cooled just below the eutectic temperature, 183. You know, this is eutectic, 183. I'm just shading it here. This is eutectic. So 183 degrees. So it says, it means our point is just a little bit below it. So it means we have to draw a what? A tie line. You draw a tie line that touches the two boundaries. Our two boundaries are what? Alpha plus beta and alpha boundaries. The boundaries. So in this case, just below 183, the closest distance you can get from 183 is we draw this line just below it. We call that tie line. So in essence, this is the line. I just drew it. Can you see R plus S? So this is the boundary we are, alpha plus beta and what? And alpha. So when you draw this just below 183, you have this. And then you give this one R and you give this one S. Are we together? So what did the question ask us to find? We asked to find what is the fraction of the alpha and fraction of what? Alpha plus beta. In this case, we have a mixture of what? This is our composition. The blue balls is the alpha, and then the alternate red and blue is the what? Alpha plus beta. So because it's within these two dual region, it means we are supposed to find the percentage of alpha and what is the fraction of this alpha itself, this blue ball, and then what is the fraction of this alpha plus beta. So this is the structure, is combination of this structure plus additional what? Alpha. This is the alpha boundary and this is the alpha plus beta boundary. So what we are asked for, what is the fraction of the percentage of alpha and percentage of the eutectic structure? This is the eutectic structure, alpha plus beta of alpha. For you to determine the percentage of alpha, we won't take R, we now take the other one, S all over the total, S plus R. For alpha is going to be S. You won't take the distance close or adjacent to alpha, you take the opposite, which is S all over the total. And what is S? You can know your distance S here. You know here is 61.9. And here is C1 is our alloy, which is 34.6. That's our S, 61.9 and 34.6. And then the total, R plus S, is going to be 61.9 minus this C alpha. And when you draw this, you can draw this, where it touches this alpha boundary, you stretch down and get the the best calibration, the closest approximation. And in this case, it's given us 18 weight of tin, so it's 18. And then so the percentage of alpha is going to be 6.62 fraction, and then in percentage is going to be what? 62.19%. So the other one, because there are two structures here, alpha, and because you know the boundary determine your structures. If for example you are working between the boundary of alpha and beta, it means your two structures are alpha and beta. This is the beta boundary. But because you are working between the boundaries of alpha and alpha plus beta, so you have two boundaries, and so your structures will now reflect these two constituents. So now when you want to determine the fraction of alpha plus beta, so you won't take the S, which is adjacent to alpha plus beta, you take the opposite, which is R. It's going to be R all over the total. And in this case, you will have it here, R all over the total. You have 34.6 minus 19.2, and you end up with 0.38. So whenever you are working within two boundaries, when you add their fraction, they must give you, their fraction must be equal to 1, or their percentages must be equal to 100%. I think that's all for this question. We look at the next question. Any question, please? So we go to the second one. The second one is still the same lead tin alloy, but you could have different diagram. There is also silver and copper. They look similar also. This is silver and copper. Also the similar diagram with lead tin, right? So the same analysis will still apply. So now the 40% by weight and 60% by weight lead at 150 degrees, right? So what phase are present? This is question number 2. You have to locate this point in the what? In the lead tin phase diagram. So this is the lead tin phase diagram. It says 40% by weight. What's the temperature? At 150. Remember, you use the left one because the left one is the degrees while the right one is the Fahrenheit. So can you see we've located our what? Our alloy. This is 150 degrees and what? This is 40% by weight. Tin is represented by what? By Sn, right? So can you see our point B? So what phase is what is the phase in at point B? What is the phase? What is the name of the phase? Alpha plus beta, isn't it? Region of alpha. So B is within alpha plus beta region. The phase present is what? Alpha plus beta. Is in the dual phase alpha plus beta. Does alpha and beta coexist in this phase? The second question it asked is what? What are the composition of the phases? Here you are not asked the percentage or fraction. What are the composition? So the alpha, what is the composition, and the beta, what is its composition? So you draw a tie line. I've drawn it already, and then you drag it down. So the composition of alpha is this. The composition of alpha corresponds to what? Corresponds to 11% by weight tin, 89% by weight what? Lead. So this is the composition of the alpha. So the first thing you look at is the region the question mentions. The question mentions alpha and beta. So here when you drag down, you will know the composition of what? Beta, which is 98% by weight tin, and then obviously it's going to be 2% by weight what? Lead. So this is the composition of beta and this is the composition of alpha. So the next question is calculate the relative amount of each phase in terms of mass fraction. So now the next one is our calculation. Now the next is the weight fraction or mass fraction of each of what? Of alpha and beta. So in that case, we draw a tie line, horizontal line that touches the two boundary alpha and beta. So let's start with alpha. This is where the alpha is going to be, R is adjacent to alpha. So we won't take R, we will take what? S. S all over the total distance. So the mass fraction of alpha is going to be S all over the total distance. And we know what is our S, isn't it? Here is 89 minus what? Minus 40. And what is total distance? You know, when we are determining for alpha, you take the opposite, which is S all over the total. And when we are calculating for beta, the fraction percentage of beta, or the fraction or percentage of beta, we won't take the distance adjacent to it, which is S. We'll take the opposite, which is R all over the what? Total. So for beta is going to be R all over the total. And you can be able to get the best estimate for your R and R plus S. R plus S is from here minus C alpha. C beta minus C alpha is your total distance, isn't it? And then when you add them up, you must have 100%. So here is 67% and here is 34%. All these calculations we are doing is in weight fraction because you see it indicated. You can see weight percentage of what? Tin. Can you see it? WT. So weight is equivalent to mass, isn't it? So we are asked to convert these answers to what? To volume, right? So when you have something like two constituents, for example, if your calibration is in what? Is in weight, it means you're able to find weight percentage of alpha and weight percentage of beta. You are asked to convert them to what? To volume, in terms of volume percent, because the calculation, the diagram itself was in weight percentage, isn't it? You are asked to determine in what? Volume. Remember that density is equal to what? Mass over volume. Mass is representing what? Weight. So whenever you have your answers in weight, you want to convert to volume. So you use this way. So your volume of alpha is going to be equal to what? The volume of alpha over volume of alpha plus volume of what? Beta. What is volume? Using this equation, volume is equal to what? Mass all over what? density. So in this case, volume of alpha is equivalent to what? Already this initial, right? Weight of alpha all over density of alpha plus VB is same thing as weight of beta all over density of what? Beta. So in this case, we come and substitute this, our initial answers, into this to get volume of what? Alpha. And subsequently, we can also do that to get that of what? But we don't know the densities. We have to come and determine our densities of what? Alpha and density of what? Beta. The question gives density of lead to be 11.23, and density of tin is equal to 7.24. So can we go directly and substitute? What is density of alpha? Is it the same thing as density of lead? Or is density of tin also the same thing as density of beta? Remember, density of lead is exactly here at this point, and density of tin is exactly at what? At the right hand side of the y-axis. But remember, our alloys are within the what? Are not at the axis. So it means we have to of alpha is not equal to density of beta, and density of beta is not equal to density of what? Tin. The composition of alpha contains lead and tin, and the composition of beta contains lead and what? Tin. So it means we have to use this formula to determine the composition of the density of our alpha and density of beta. Because density of alpha is not the same thing as density of lead. It's only equal when the region is within the origin. When it is at the origin, then density of lead is equal to what? When it is at the origin, then density of lead is equal to density of what? Beta. When it is here at the last vertical line, then density of, so what actually happens is here is lead and here is what? Tin. This is the only point where lead is 11.23, and this is the only point where tin is 7.23. So in between, lead will begin to decrease till it reaches to what? 7.24, isn't it? Or tin begins to increase till it reaches to what? 11.23. Is it clear? Our alpha and beta, they are within this region. It means we'll have to find their densities. So this is the region of alpha. So this is our actual alpha. You know, it's around here, which is what the composition of is 11% by weight tin and 89% by weight lead. So we use this 11 and 89. So when you pick 11 here, it means it is going to be over the density of what you are mentioning. 11% tin, isn't it? It must be over density of tin, right? And then here for the C2 here composition here is going to be what? Whatever one we take, it has to be over its density. So 89% by weight what? Tin, lead over its density. So this is density of alpha. And secondly, that of beta is within this region. Can you see? This is our actual beta, which is 98% by weight tin and 2% by weight lead. So whichever one you pick, 98% by weight tin over density of tin and 2% by weight lead over density of what? Lead. And so this is our density of what? Beta. And then we can finally come and substitute in this equation, right? We are determining our weight of alpha and weight of beta, isn't it? This is the weight of alpha and weight of beta. And then the density of alpha, we determine it here, and density of beta, and so we can substitute, isn't it? Is there any problem? And then for beta also, you do the same thing. It's going to be volume of beta all over volume of alpha plus volume of beta. And then you substitute weights, and you have it. So we stop here, class.